last lecture I discussed with you about the solidification behavior of an alloy, ternary alloy, in which you have two eutectics, binary eutectics and one isomorphous system exist. And actually I use this as a model, and I have been discussing with you for 3-phase equilibrium in ternary system using this model. Now, you know there are many ternary 3-phase equilibria possible, like you can have a periodic reaction between at least one of the binaries can have a periodic reaction, other binary can have a eutectic, and third one can have isomorphous, or in fact one of the binaries can have monotectic reaction possible. But these reactions and also the equilibria are a little bit more complex, so that is why I am not discussing. But one of the things which is a corollary of the things which I have discussed in the last 3 lectures is that you can have a ternary system in which two of the binaries will be isomorphous and third binary will form eutectic systems. So, the thing which I am trying to say is like this. Suppose you have a ternary system like this, in which you have 3 binaries, and 2 of them form isomorphous system, 1 of them form eutectic. I am talking about that. So, in this case how the space model will look like, and also how the isothermal sections will look like. Okay. So, as you see here, this is alpha, this is alpha, this is beta, this is beta. Okay. So, and this is alpha plus beta. By looking at this diagram or this picture, you can understand that these two are isomorphous. So, they are miscible, A and C are miscible in all compositions, all concentration, B and C are miscible in all concentrations, both in liquid and the solid state. So, that is no problem. When I put AC and BC binaries together, that is no issue at all, correct. The problem is that what will happen to this eutectic, okay, whether the eutectic will expand in all concentration ternary compositions, or it will have a limited existence inside the ternary triangle. That is what is the important aspect you have to realize. Okay. The point I am trying to make is that what is the extent to which the eutectic will solubility gap between alpha and beta will extend inside this ternary triangle, inside in the ternary composition. That is what is the important thing. Well, let me just draw these phase diagrams. First, the space model. Space model is very important. I am going to draw it, then I will discuss further. So, space model is what you have been learning from me for the last 5-6 lecture. Before drawing, I would like to tell you that it is always easy if you can draw the space model and think in 3 dimension, but it is not the case always. So, A and C will form a isomorphous system, right, T A and T C. B and C also form isomorphous system, but I will not draw the whole thing fully. Why? Because it will look nice, you can see many things. These are the 2 cut pieces, it indicates that you have a isomorphous system. Okay. Let us not draw it. And between A and B you have a eutectic. How to draw that? Obviously like this. Correct. So, that is how it will look like. So, this is the eutectic point E, and this is C, this is D. These are sitting on the binary, remember that, because each one is a binary. Okay. We have just put these things up, we have taken these pieces up and made the triangle. The question is that whenever you such a thing available to you, the question you always ask is that how much inside this ternary triangle this miscibility, this gap of solubility between alpha and beta will exist. Okay. This is alpha and this is beta. Well, it has been observed that because of addition of these three third element C, remember this eutectic is between alpha A and B. Okay. So, because of addition of this third element C, eutectic temperature will go down quite a bit, it will not go up. One point I will like to tell you, for in ternaries or in quaternaries whatever, whenever you add a third or fourth element, normally the binary eutectic temperature goes down, it is just like a Raoult's law or whatever. So, here also eutectic temperature will go down and this will be like this. Okay. This is E1, it will go down till E1. Why it will go down? Remember E is sitting on the binary, right, this is the binary composition. E1 is sitting inside the ternary, okay, somewhere there, corresponding to this composition. Now, one can actually draw this these things, these triangles to show, or let us draw it by yellow chalk. What I mean to say is that you can have this triangle. What does this triangle mean? Okay, let me draw it little larger way. I have drawn the triangle in such way that one of the corner of the triangle is sitting on the E1 line. Remember, this is the binary, this is the extension of the binary eutectic inside the ternary. So, this is what the liquidous surface is changing the slope, it is going down, it is just like a heel, it was just like a heel, it is going down. Okay. So, this is the liquid composition L, this is the alpha composition, this is beta composition. So, you can clearly see that 3 phase equilibrium can be represented by this triangle again. So, that is the critical feature of the ternary phase diagrams having 3 phase equilibrium. This will be given by a triangle, or this is a triangle. Okay. So, one can draw many such triangles. Okay. In fact, one can actually take these things little bit this way. Okay. I think I have made a small mistake, things are okay, I have just made a small mistake to connect these points. This will be green chalk is better, otherwise you will not see it. Okay. So, then what will happen? This one will meet here. So, what does it mean? The solubility difference between alpha and beta is extending just like this. That is how it can be drawn. If I project this thing, so what is happening that if I adding C element into the binary AB, this is how the liquidous surface is going down and it is reaching a minimum point E1 at which the eutectic is stable, or other alpha and beta phases can be differentiated. Beyond E1, it is alpha and beta phases are indistinguishable. Why? Because their composition and things are not differing much, that is why. So, beyond E1 you cannot have, basically it goes little bit up also. So, one can actually draw, it comes down and goes up, this C1 here. So, C1 is the critical point. I will explain what is the meaning of C1. C1 is the critical point at which this is E1. So, this will be, so if I draw it this way, many such things. So, it is just like that. E1 C1, then it is clear. So, basically what does it mean? It means that liquidus temperature is going down, and at a temperature corresponding to E1, E1 is same at C1 actually. Let me tell you, there is a pop up of compositions beyond E1. Some zone is exist where alpha and beta is distinguishable, but beyond C1 composition more than C1 or above C1 this side alpha beta is indistinguishable. So, one can actually write down this is like this is alpha plus beta and this is alpha plus beta, but this beta is indistinguishable, that is why. So, what does it mean? This beta is indistinguishable between from alpha. Okay, that is the point you must try to remember. Now, let me just try to draw the isothermal sections. I think it is possible to draw it here one by one. This is at temperature T1. At T1 you have only, obviously you will have beta, beta is the highest melting or B is the highest melting elements, beta, and then you have liquid plus alpha, liquid plus beta, sorry, and liquid. Okay. And at higher lower temperature, this is T1, at T2 it will be like this. Liquid, liquid plus beta, alpha plus liquid. It will extend till further lower temperature T3, okay, A, B, C. This will be little bit here you are going to see this triangle whatever I have drawn here as a projection. This is the triangle which will exist, and then you can actually connect these 2 points. So, this is alpha plus beta plus L, and this is alpha plus L, liquid beta plus L, okay, and further up is alpha plus beta. So, this is at T3. T4 will have similar things. No, it will be different. That is what you are going to see this interesting thing that what I have drawn here at the bottom, and this will be like this. Okay. Then you have a zone like this, and this is the point C1. So, therefore, this is alpha plus beta eutectic, which is extended from the Barnett inside the ternary, and this is alpha, this is beta, and this is the point C. Okay, this is the point C, not C1, C, right to C. Okay. And then you have a liquid and alpha plus liquid, sorry, I should use the same color, alpha plus liquid. Actually, one can write even better way, because you cannot distinguish between alpha and beta. So, that is why you have to write like this. Whatever beta or alpha will form inside the liquid in between with equilibrium with a liquid will not be distinguishable from the alpha. Same thing will propagate. So, T5 at temperature T5 same thing will propagate. this is alpha plus beta, and here this is liquid induced with alpha beta and alpha, just like this. Okay. So, now we have gone lower temperature, so that C point is below the C point. So, it is much lower this point C wherever it is sitting, and at still lower temperatures T6, solidification will be over, and what will happen? You will have a zone in which alpha beta eutectic will form, beyond which only alpha will form. So, by looking at this isothermal section, you can clearly understand what will happen to 3-dimensional thing. So, only thing critically important is that because you are extending this eutectic point inside this ternary Gibbs triangle. So, therefore, this extension will lead to a point in which beyond which alpha and beta is indistinguishable. You cannot distinguish them between, because composition will be similar, macrostructure also will be similar, nothing will be distinguishable, and that extends, that moves on from these to these points, correct. So, that is what will happen, and as I told you, this feature, triangular feature keeps on moving, keeps on seeing only at not moving, only seen at this temperature. Beyond that, you have not more 3-phase equilibria exist. Basically, this 3-phase equilibria is telling you that eutectic reaction is taking place here, beyond which there is not much eutectic reaction, only alpha or whatever, alpha or beta, which are both are indistinguishable from each other, precipitating out from the liquid. Okay. So, this is one of the variations of the phase diagrams compared to the one I have taken as a model and discussed. This is also important in the sense that this is more frequently observed. As I told you, the important system like what? Bismuth, antimony and lead. No, this is not. Bismuth, antimony and lead will be having system which I discussed. Bismuth antimony forms isomorphic system, bismuth lead form eutectic, lead antimony form eutectic. Okay. But such a kind of system do exist, I am not able to remember right now, I can tell you later on. Such a kind of system actually are existing, quite many metallic systems actually show this kind of behavior. So, now let us, so that is about the 3-phase equilibria. So, in the subsequent lecture, I am going to discuss with you about the 4-phase equilibria, and I think let me tell you the whole plan for the lectures which I am going to take. From next week onwards, you are going to see, not next week, there are about 10 more lectures which you are going to see in this course. Obviously, because I have finished the single phase equilibria for ternary, 2-phase equilibria for ternary, 3-phase equilibria for ternary. Now, I am going to also discuss about 4-phase equilibria for ternary, and then I am going to tell you about some important ternary system like stainless steel and some of the ceramic systems also, and that is how we wind up the whole course. And you will have end semester exam, or the final exam is on 24th of this April and also 2nd of May. No, not 2nd, 24th and 31st of April. So, you will get a 1 week time to study. We will not have any lectures or these assignments. That is how I have planned. So, in the 4-phase equilibria, as you know, 4-phase means what? In a ternary system, 4-phase equilibrium means it is an invariant point, because obviously, because in a ternary system you have 3 components. So, maximum number of phases which can coexist in a 3-component system is 4, according to the Gibbs phase rule, correct. So, what are these 4 phase equilibria. So, maximum number of system, maximum number of phases is basically 3 minus 3 plus 1, sorry 3 4 plus 1 is equal to 0. So, maximum 4 phases can coexist in a ternary system as opposed to 3 phases in a binary systems. So, 4 phase equilibria means what? That situations where these 4 phases are under equilibrium. So, there are actually, if you consider only liquid solid systems, there are actually three important reactions. One is this one, what is known as ternary eutectic. Other one is ternary quasi peritectic, alpha plus liquid going to beta plus gamma. And last one is the peritectic. So, there are 3 different 4 phase equilibrium systems can exist. This is straightforward. This is a ternary eutectic. To give you example, aluminum, copper, silicon forms a ternary eutectic, alpha aluminum, silicon and Al2Cu. This is a very complex type of things. In neither a peritectic reaction nor any other thing, this is looks like quasi peritectic reaction, and most of our cases is case bypassed. There are situations. This is a ternary peritectic reaction, it occurs in some of the systems. I am going to, in the subsequent lecture, I am going to concentrate mostly on these ternary eutectic system, not only because it is observed frequently, but also it is easy for students to understand. I will give you some light on these or this, okay. They are also important, but we will not go in detail of these two reactions. This will be the most important reaction which I am going to discuss. Okay. As you know, it is a obviously if you want to have a ternary eutectic systems, either you need to have all the 3 binaries have eutectics, then you have a ternary eutectic inside it, or 2 binaries will have eutectic and third one will have some other reaction like peritectic or things. So, but we are going to take simplest one, that is we are going to consider 3 binaries in which all of them has binary eutectic between themselves, like A, B, B, C and C has binary eutectics, and we will discuss. So, that is what is the plan for the next 4 or 5 lectures.